The next step in our discussion of hypothesis tests is thinking about situations where we actually have two samples instead of one. In this scenario, for example, the teacher has two sets of test results and wants to see if there's a difference between the two. So, in other words, if the results that she gets from the new method are somehow different from the results she got from doing things the old way. So we have here our two samples and two population proportions. Now I'll use P1 for the proportion of students who met some benchmark in this year's class, right? And P2 for the proportion who met the same benchmark in last year's class. Okay, now one of the nice things about these two sample comparisons is that the null hypothesis is very consistent. It will always be P1 equals P2, or equivalently, P1 minus P2 equals 0. Now, the alternative hypothesis, on the other hand, will be either greater than, less than, or not equal to, depending on the specifics of what our claim is. All right, once we've calculated our data, once we've collected our data, the testing process is going to follow exactly the same procedure we saw with our one sample situations. We're going to calculate a test statistic and either compare that to a critical value or use it to calculate a p-value, then compare that to our alpha value. The only real difference is going to be in how we calculate that test statistic. Just like all of our other scenarios, there's going to be a formula that we use. So I've laid out here all of our variables. P sub I will be the population proportions. X sub I and N sub I will be the number of successes and the size of each sample. And P sub I hat will be the corresponding sample proportions. And I'm just using I to represent the two samples. Since we're only looking at two, it's always going to be either a 1 or a 2. So this P bar variable here, that's a new one that's unique to situations with two samples. It's the so-called pooled sample proportion. Now, if you look at the calculations, what we're doing is adding the successes from the two samples and dividing that by the combined size of the two samples. In other words, you can think of this as the proportion of successes we would get if we combined the two individual samples together into one kind of super sample. Now, if we assume that the two population proportions are equal, which is what our null hypothesis says, then the best estimate of the combined populations is what we get by combining the two samples into one big sample. So P bar is the estimator of the combined sample proportion. And referring back to my teaching example, this would be the population made up of all of the students together, regardless of the method the teacher used with them. Okay, now if we also assume N1 times P hat 1 is greater than or equal to 5, and N1 times Q hat 1 is greater than or equal to 5, then the distribution of P hat 1 can be approximated by a normal distribution with a mean of P1 and a variance of P1 times Q1 divided by N1. And of course that applies to the second sample as well. All right, so because the two samples are approximately normal, right? That means that the difference, P1 hat minus P2 hat, will also be approximately normal, with mean equal to P1 minus P2, and variance, let's see, sigma squared, right? Variance sigma sub P1 hat squared plus sigma sub P2 hat squared. Okay, now referring back to what we did up here, right? This is the same as P1 Q1 over N1 plus P2 Q2 over N2. All right, and this is all based on the property that the variance of the differences between two independent random variables is the sum of their individual variances. Now, remember what we're assuming based on our null hypothesis. We're assuming that P1 and P2 are equal, and the best estimate of their common value is this P bar. Right? So, if we replace P1 and P2 with P bar, and Q1 and Q2 with Q bar, and then take the square root of both sides, we get this formula for the standard deviation, right? So, to summarize, we know that the distribution of P1 minus P2, which is what we're trying to conduct a test for, right, is approximately normal with mean P1 minus P2 and standard deviation given by this formula. Right? These are the values that we're going to use to calculate our test statistic. So now we have everything we need to do our test. Right? I've defined all of our variables on the left side here, just like they were on the previous page. And we've got our standard requirements. Right? If you flash back to when we talked about testing a hypothesis for a single sample proportion, they had exactly the same requirements for the sample and the number of successes and failures. That's the N1 P1 greater than or equal to 5, N1 Q1 greater than or equal to 5, right? The only new thing is the requirement that the two samples have to be independent. And we're actually going to talk about the situation where the two samples are somehow paired later on in this chapter. And finally, we've got the formula for our test statistic based on the distribution of the difference of the populations, right? P1 hat minus P2 hat is the difference of the sample proportions. P1 minus P2 is the mean of the distribution. And this square root in the denominator is the standard deviation we calculated on the previous slide. Finally, since the null hypothesis assumes that P1 and P2 are equal, their difference must be 0, so the formula simplifies to the right-hand expression. All right, so as I said earlier, the actual testing process is going to follow the exact same pattern that we saw when working with a single sample. In the next lecture, we're going to look at some specific examples and see how to do this with two sample proportions.